Hello, Michael. It's Dr. Fred Fizzle here, and today I'm going to be talking to you about nerve impulse transmission. Now, in my last video, I was discussing with you sort of the structures of various different neurons, but I didn't say how these impulses, what they actually are, and how they're actually spread across the actual neuron. So what I've drawn for you here, as you can see, there's a diagram. In means inside the cell. Out means outside the cell. That these things that say open here is just an open channel. This is a closed channel, and this is this is basically a pump. Now, you're probably thinking a pump in a cell membrane. What's then the difference between that pump? Because that pump looks very similar to an ordinary channel. So what actually is the difference? Well, the difference with a pump and a channel is that a pump actually uses energy from ATP to actually move the ions across it, whereas a channel relies on a passive process of diffusion from an area of high concentration to an area of low concentration. Now, how is an impulse started? Well, it's started by a stimulus. We know this before from the last video, we should know. So I'll write up here probably stimulus. That's the first thing that happens. So what does the stimulus actually do? Supposing this is our cell membrane, what does this stimulus actually do? Well, it leads to more channels becoming open. I've drawn you an example of an open one here and a closed. It doesn't actually necessarily mean that this would be the case. Following a stimulus, they'd all gradually open. There'd be absolutely loads of these. The point I'm making is that this is only a small section, and this is just to show you really what these different types of channels are. It's not to show you that how many are open after a stimulus or anything like that. It's just to give you a representation of what a membrane would actually look like with these channels in it. Okay, so once we have our stimulus, what's going to happen initially is more of these sodium ion channels are going to open. Okay, so I've drawn you an example of an open one there. So our sodium is going to there's going to be an influx of sodium. An influx means moving into the cell from over here, from outside the cell. So over here I'll draw some Na+. Okay, pen's not particularly brilliant, but yeah, anyway. Na+. Na, by the way, in case you haven't noticed, is the symbol for sodium. So if you look in the periodic table, you should be able to find that. So sodium builds up here, and after a stimulus, what stimulus does is it deforms these channels to enable them to open. Once these are open, of course, sodium's going to move from an area of high concentration over here to low concentration inside the cell over here. So the sodium will diffuse in, but initially only a few of these will be open, and the ones that will be open will just be called sodium channels, sodium ion channels. Okay, so once a few of these sodium ions are over here, I'm not actually going to draw them over here, but just pretend that they are over here. What's going to happen is basically that's going to lead to a change in voltage, and once that starts to happen, that will lead to some special channels called voltage-gated sodium ion channels opening. But they'll look very similar to this, but they'll be controlled by voltage whether they're open or not. And basically what I forgot to mention is that when ions actually move into the cell, because these are positive ions, they're actually going to increase the potential inside the cell. So as these sodium ions diffuse into this cell, the potential is going to increase gradually. Okay. So that increase will stimulate these voltage-gated ion channels to actually open to enable more sodium ions in. Now, over here I've drawn some key words. Let's not forget these. Resting potential is what happens before a stimulus actually arrives. So I'll discuss that with you at the end, because I've already said that there's a stimulus now. Stimulus up here. So now that there is a stimulus, once quite a few of these sodium ion channels are diffused in, and the voltage-gated ones are opened, and some more are diffused in, eventually the threshold level is basically where some of them have diffused in, so that it gets to the point where an action potential is going to happen regardless of anything else. The threshold potential is usually around minus 50 millivolts, okay, which is basically just a difference in potential from inside the cell in relation to outside the cell. Obviously, as I've just said, the cell potential is going to change, which is going to stimulate voltage-gated ones to open. I forgot to mention that the resting potential actually is minus 70 millivolts. That might help you to understand, because as you can see from here to here, it's increased because of this influx of sodium ions to minus 50, which will stimulate these voltage-gated ion channels to open. then what will happen is this threshold potential we raise to something known as action potential at plus 40 millivolts. Now once this action potential is actually reached, these sodium ions will actually diffuse from inside the cell along the neuron, and then what will happen is the same process will continue, and that will lead to this sort of conduction, if you like, or transmission of the neuron along of the action potential, sorry, along the neuron. Okay, so basically what will happen is once these are open here and the potential's been altered, it will just have a reverberation type effect all the way along the neuron. So this nerve impulse will be transmitted all the way along the neuron. Now, I've mentioned here resting potential at minus 70 millivolts. Now, how is that actually maintained? Because you'd think that with these influx of sodium ions, that the potential will continue to increase to plus 40, but then once the action potential is finished and has spread down the neuron to send off the signal that it wants to send, how will that actually be restored to the resting potential? So first of all, I should probably mention that this process is known as depolarization. Okay, depolarization. Now I emphasise the D bit because once this plus 40 millivolts has been reached, the complete opposite happens. So take it back down to minus 70 millivolts, and this is known as repolarization. Okay, so you've got a depolarization and a repolarization. But once our how does this repolarization occur then? Because over here our depolarization, as we know, occurs because Na plus ions are influxed, which basically means they moved into the cell. So there's an influx of these Na plus ions. Repolarization occurs because there's an efflux. You probably might not have come across that word before, but efflux of K plus. Now K plus, for those chemists out there, will know that these are potassium ions. So you should know that an efflux of potassium ions, which is the moving out of potassium ions, it doesn't take a genius to work out that will reduce the potential again. So once these plus ions have actually increased this potential up from minus 70 millivolts up to plus 40, there'll be an efflux or moving out of potassium ions along this concentration gradient that way to outside the cell, will cause a repolarization effect which will decrease the potential. Okay, so that's essentially how depolarization and repolarization actually occurs. I know that's a lot of information to take in, but it makes logical sense. So as long as you revise it, you should be able to work it out. Saltatory conduction, I forgot to mention, is basically where because these sodium ions are diffusing sideways along the neuron, as I mentioned before, they almost move in a jump-like motion. But this can only happen if the neuron's actually insulated by something known as a myelin sheath. Now I'm not going to go into sort of the structure of the neurons and the myelin sheath. I'll probably do that in the next video, discuss the actual purpose of the myelin sheath and how some neurons have it and some don't, and what the effect of it is. But all you need to know for now is that the neurons use this method of saltatory conduction to speed up the transmission of nerve impulses. Down here I've wrote all same size. Now this is to remind me that all the actual action potentials that are sent down this neuron have the same intensity. Each individual one has the same intensity. I have to be careful of saying that because collectively, if there's a more frequent nerve impulse being sent down this neuron, then the brain's going to get more regular signals, and it's going to interpret that as a stronger stimulus. So it'll bring about a sort of more exasperated, if you like, change to bring about where this depends what kind of reaction that the body's actually involved in for this particular scenario, because it might be involved in a negative or a positive feedback system. So if it's a positive, it's going to bring about a more intense change in order to continue the effect that has already taken place. So I'll use an example that isn't correct in the body for this. Like assuming our bodies wanted as much glucose in them as possible, there'd be no rational explanation for this, and this is wrong. Our body doesn't want as much glucose as possible. But assuming it did, then this would use a positive feedback to continuously increase the amount of blood glucose level, wouldn't it? So what this will mean is it will mean that this a more intense stimulus being sent down these nerve impulses will bring about a greater change to the amount of blood glucose levels than assuming that this nerve impulse wasn't as frequent, that these individual action potentials didn't occur as frequently, would result in less of a stimulus change. Okay, that's a very complicated concept, and I probably didn't explain that as clearly as what I should have done. But the main point is, it is basically the more frequent these action potentials are sent, the greater the reversal or the greater the increase in change that the brain brings about. Okay, so obviously for a negative feedback system, that the change will try and be reduced, and positive, that the body will want to increase the change that's already taken place. Will want to increase the effect of that stimulus that is already there. Okay, so basically that's what the all or nothing principle is. It is the fact that once the threshold potential is reached and the voltage gated ion channels start to open, that's it. It's gonna go up to plus 40 millivolts, regardless of what happens next. It's just gonna happen every time. So it's gonna either not get there because not enough sodium ion channels have opened because the stimulus wasn't strong enough, or it is gonna get there and it's gonna be sent. So all these action potentials, are going to be the same intensity, are going to have the same magnitude. The only difference is that the brain will actually detect how frequent these are and bring about a change that actually it will interpret that as the strength of the stimulus and bring about a change appropriate to the degree of intensity that the stimulus has. Okay, so this is essentially how our communication system in the body works. It's a very complicated system, as you'd expect. Because our bodies are very intricate and wonderful things. Hope you've enjoyed this video. In the next one, I'll probably go over what this myelin sheath is actually used for and how it brings about this increase in speed. But for now, I'll leave you with that. So goodbye.